Hello everyone, this is Gokul RR of second year ECE. Today in this video we are going to see about Cascode Amplifier. First I will give a brief introduction, then we are going to stimulate DC and AC analysis in ECEDA software. Come, let us go inside the video. Introduction. Here basically we have two type stages of amplifier. The first one is single stage and the next one is multi-stage amplifier. Generally, single stage amplifier contains single transistor for amplifying a weak signal, whereas multi-stage amplifier contains two or more transistors for amplifying a weak signal. For example, common emitter belongs to single stage, and Cascade and Cascode belongs to multi-stage amplifier, and this circuit have a lot of advantages over the single stage amplifier, and this amplifier is generally constructed using FET or BJT. In this video we are going to construct using BJT. In multi-stage amplifier, Cascade faces certain issues, so Cascode amplifier is introduced to overcome the drawbacks of Cascade amplifier. Now we are going to discuss about Cascode amplifier, its design, and why we use two different configurations in it. Generally, Cascode amplifier is a multi-stage amplifier that consists of common emitter configuration and common base configuration. The transistor Q1 and its associated components operates as common emitter amplifier stage, while the circuit of Q2 functions as common base output. In this circuit, we have 5 resistors and 3 coupling capacitors and 1 bypass capacitor. Here, common emitter configuration is placed in input side to obtain high input resistance. Meanwhile, we placed common base configuration in output side to obtain higher bandwidth. Compared with Cascade amplifier, the bandwidth is higher for Cascode amplifier. So this is the main advantage of common base configuration in output side. Cascode amplifier gives higher bandwidth and moderate gain. Features of Cascode amplifier. Advantages. Here we have Cascode amplifier provides high input impedance. It provides high gain. It provides higher bandwidth compared with Cascade. It provides high output resistance. It gives high skew rate and high stability. Limitations. The only one disadvantage of Cascode circuit is it requires 2 transistors and requires relatively high supply voltage. Application. In the RF tuners, Cascode amplifiers are used. Amplitude modulation technique uses cascoding techniques. Now we are going to deal with DC analysis. Here we have an example problem of DC analysis, and here we have a DC analysis circuit diagram. From the circuit diagram we can find 2 transistors of BC107 and 5 resistors with voltage supply 12 volts, and it is grounded. For transistor Q1 we have 3 nodes, VB1, VE1 and VC1. Similarly for transistor Q2 we have VB2, VE2 and VC2. In Cascode amplifier, the transistor Q1 and Q2 are connected in series, so we have the current values will be same across the resistors. Now from the question we are going to see the given values. R1 equal to 58.8 kilo ohm, R2 equal to 33.3 kilo ohm, R3 equal to 7.92 kilo ohm, RC equal to 7.5 kilo ohm, and RE equal to 500 ohms, beta is equal to 100, VB is equal to 0.7 because we are using silicon in a transistor, VCE equal to 4 volt. So we are going to determine VB1, VB2, VE1 and VE2, VC1, VC2, ICQ, IB and Q point. Now let's enter into the theoretical calculation of DC analysis. First we are going to determine VB1. Here we have a VB1 in the circuit. For finding VB1 value, I am going to apply voltage divider rule. Voltage divider rule is defined as voltage across the resistor into supply voltage divided by total number of resistors. So for VB1, we have voltage across the resistor is R3 and supply voltage is VCC 12 volt and total number of resistors are R1 plus R2 plus R3. In given we have all the values. After substituting we will get VB1 is equal to 0.95 volt. Similarly we are going to find VB2 using voltage divider rule. Here the voltage across the resistor is R2 and R3. So the formula will be R2 plus R3 into VCC divided by R1 plus R2 plus R3. Similarly, we have the values in the given. After substituting, we will get VB2 is equal to 4.9 volt. With this, we have found VB1 and VB2 values. Next, we are going to determine VE1 and VE2. So, we have the formula that VBE is equal to VB minus VE. VBE is known as potential difference. The potential difference between two voltages is known as VBE. From this, we are getting VE1 is equal to VB1 minus VBE1. After substituting the values from the given, we have VE1 is equal to 0.25 volt. Similarly, we are going to find VE2. VE2 is equal to VB2 minus VBE2. So, we have the value as VE2 is equal to 4.2 volt. From this formula, we have found VE1 and VE2. Next, we are going to determine VC. Similarly, like VE, here too we have a formula for finding VC. VCE equal to VC minus VE. VCE is a potential difference. Potential difference between two voltage point VC and VE is known as VCE. From that, we are finding VC1 is equal to VCE1 plus VE1. After substituting the given values, we will get VC1 is equal to 4.25. Similarly, for VC2, we will get VC2 is equal to VCE2 plus VE2. From that, after substituting the values in the formula, VC2 is equal to 8.25 volt. Now, we have found VC1 and VC2. Next, we are going to determine ICQ1 and ICQ2. For determining ICQ1 and ICQ2, now we are applying KVL at output side, so we will get VCC minus ICRC minus VC2 equal to 0. From this equation, we are getting IC is equal to VCC minus VC2 divided by RC. After substituting the given values, we will get ICQ is equal to 0.5 milliampere. As I said before, the transistor Q1 and Q2 are connected in series. We will have the collector current and the emitter current will be same. So ICQ is equal to IEQ equal to 0.5 milliampere. Here I generally mentioned ICQ. Here the value of ICQ is 0.5 milliampere, which is for both transistor Q1 and Q2. So ICQ1 is equal to ICQ2 is equal to 0.5 milliampere. Next, we are going to determine IB. Here we have a formula IC is equal to beta IB. From the formula, we are getting IB is equal to IC divided by beta. From this formula, we can get IB values. Next, we are going to determine Q point. While designing the biasing circuit, care should be taken so that the operating point will not shift into saturation region or cutoff region. For finding Q point, we should know IC and VCE value. Here we have IC and VCE value as 0.5 milliampere and 4 volt. So Q point value is 0.5 milliampere, 4 volt. The Q point values will be same for the transistor Q1 and Q2. With this, DC theoretical calculation is over. After stimulation, we will compare theoretical and experimental values. Now we are going to deal with a small signal analysis circuit. This is a cascode amplifier circuit that we saw before. From this, small signal analysis equivalent circuit of cascode amplifier is derived. Instead of transistor, we have replaced a hybrid pi equivalent circuit in a small signal analysis equivalent circuit of cascode amplifier circuit. From the DC analysis, we are finding the small signal parameters like R pi and GM. Now we are going to determine GM. we have a formula that Gm is equal to ICQ by Vt. From the theoretical calculation of DC analysis, we found that ICQ is equal to 0.5 milliampere divided by Vt is a constant value 26 millivolt. From this, final answer we got as 19.23 milliampere as Gm value. In a similar way, we are going to determine R pi. Here we have a formula that Gm R pi is equal to beta. From that, R pi is equal to beta by Gm. Beta, we know the value, it's 100 divided by Gm. Gm just before we found that 19.23 milliampere. Just dividing, we get R pi value as 5.2 kilo ohm. From this, we have found the small signal parameters R pi and Gm values. At last, we are going to deal with frequency response. Here we have a frequency response circuit. In this, we have 2 transistors, 5 resistors and 3 coupling capacitors, which are C1, C2 and C3, and we have C4 as a bypass capacitor. Here we have supply voltage in input and we have V in and V out. After stimulating this circuit, we'll get a model graph like this. The graph is plotted between frequency and voltage gain. In Cascode Amplifier, since we are using common base configuration in output side, so that we obtain a high bandwidth, and this is a main advantage of Cascode Amplifier when we compare with the Cascade Amplifier. And then we are using common emitter configuration in input side, so that we'll get a moderate gain and we'll get a high input impedance. This is the one of the advantage of common emitter configuration, so that it is placed in an input side. So finally we use common emitter configuration in input side for high input impedance and common base configuration in output side for high bandwidth. Well, we can see the high bandwidth and moderate gain during the frequency response stimulation in ECEDA software. So next we are going to stimulate DC, AC and transient analysis in ECEDA software. Come, let us go to ECEDA software. Now I have entered into ECEDA software and this is the home page of ECEDA. First, I will say how to create a new project. Actually, we are going to work in stimulation mode. So we should change the standard mode to stimulation mode. Now for creating new project, we are going to File and click New and click Project. So we will have a box like this. In this we need to enter the project name and save. I have already created the project, so we can move towards it. Now we are going to stimulate DC analysis. For stimulation, we need components. So I will show where the components are available. Click here and we have components like ground, VCC, resistor, capacitor, oscilloscope, function generator, voltage source, current source, LED, transistors, etc. If any specific component is not available here, we can search that component in SPICE library. Now we have taken 2 BC107 transistors and we are going to take 5 resistors. Click the component, drag it. To rotate the component, use R key. Now I am going to change the values of resistors. Click on the component and we can change the values. Now I am going to connect the resistors and transistor using wire. Now I am going to connect voltage supply here. And I am going to change it as VCC. I am going to give 12 volts and I am going to ground it. I am going to label the nodes. Now I am going to stimulate DC analysis. For that I am going to file and saving it. I am going to stimulation and stimulation settings and DC output. I am going to run it. After stimulation of DC analysis, we got the value of VC1, VB1, VE1 and VC1, VB2. Similarly, we got the values of IB, IC, VBE, VBC, VCE, beta, GM, RPi for transistor Q1 and Q2. We can copy and paste the values in Excel and we can change the format from scientific to general. We are going to compare the theoretical and experimental values. Now I have listed out theoretical values and experimental values. From this Excel, we can compare the values of theoretical and experimental. Now we are going to stimulate transient analysis. Now we are going to place voltage source in input side. We can also use function generator and oscilloscope instead of voltage source if we are going to stop with transient analysis alone. But we are going to stimulate frequency response too. So we need to use voltage source in this software. In DC analysis, we have shorted all the capacitors. But in transient analysis, we need 4 capacitors for getting AC signal as output. Here C1, C2, C3 are coupling capacitors and C4 is a bypass capacitor. Now I am going to ground C1 and I am going to connect load resistor in C3 and I am going to ground it. Now I am going to change V1 as Vin. Now I am going to change DC to sine. Here I am going to change 10 millivolt and frequency as 1 kHz. Now I am going to insert probe. Now I am going to save the project and I am going to stimulate it. Transient, stop time 10 milliseconds and start time 0. I am going to run it. So here we have the waveform for 1 kHz and we should see peak to peak voltage values. So we can see Vin and Vout graph separately. For that, go to waveform, click waveform configuration and click V0 as 2 and we can change the color. After changing color, we can give apply. This is Vin graph and this is Vout graph. And here we have 180 degree phase shift in which Vin is positive and V0 is negative. Because we have placed common emitter in input side, so the input signal will be 180 degree phase shifted and the output signal will be given as input for common base and it will not make any 180 degree phase shift change. So we got the 180 degree phase shift in graph. Here in this peak we have 167.075 millivolt and in this peak we have minus 171.979 millivolt. To find frequency response, we can vary frequency from Hertz to megahertz. For example, I will vary from 100 Hertz. Here I changed frequency to 100. Here we have the graph. Here in this peak we have 105.66 millivolt and in this peak we have minus 70.283 millivolt. Next we will try for 400 Hz. Here I changed frequency to 400 Hz. This is the graph. Here in this peak we have 161.471 millivolt. Similarly for this peak we have minus 167.776 millivolt. Now compared with 100 Hz, the voltage value is being increased. So next we will try with 10 kHz. Now I have changed frequency to 10 kHz. Here we have the graph. Here we have the peak value as 164.273 millivolt. Similarly, for this peak, we have minus 173.38 millivolt. So from 400 Hz to 10 kHz, the voltage value is almost constant. Now let's try with 100 kHz. Now I changed frequency value to 100 kHz. And here we have the graph. So we have the peak value as 161.471 millivolt. Similarly, in this peak we have minus 178.984 millivolt. So we have the voltage value constant from 400 Hz to 100 kHz. So next we will try with 1 MHz. So now I changed frequency to 1 MHz. So here we have the graph. And here we have the peak value as 116.637 millivolt. And similarly here we have minus 118.739 millivolt. Now the voltage value is getting decreased. So the value increased from 100 Hz to 400 Hz and became constant from 400 Hz to 100 kHz and started decreasing from 1 MHz. So we will see the frequency response graph in AC analysis. At last, we are going to deal with AC analysis. For that, I am going to click this voltage source and I am going to remove this frequency and I am going to enter 1 in AC amplitude. Then I am going to file, save. Then I am going to simulate AC analysis. Number of points 100, start frequency 1 Hz, stop frequency 1 GHz. Now I am going to run it. Here we have the graph. From this graph we are going to find gain and bandwidth. So here we have the maximum gain as 24.906 dB. Next we are going to find bandwidth. Bandwidth is equal to higher cutoff frequency minus lower cutoff frequency. For finding higher cutoff and lower cutoff frequency, maximum gain minus 3 dB. So we have the bandwidth as 956.53 kHz, nearly to 1 MHz. So comparing with Cascade, we got moderate gain and high bandwidth. So we have stimulated DC analysis, transient analysis and finally AC analysis. We can also download this waveform in PDF format. For that, go to waveform and click export waveform. We can also download the circuit in PDF format also. So go to file, click export and click PDF. The file will be downloaded. So in Cascode Amplifier we have moderate gain and high bandwidth.